in this class, one of the things that you are going to be responsible to be able to do is to understand and draw and interpret graphs of position as a function of time, velocity as a function of time, and acceleration as a function of time. Today we're going to start with position as a function of time. It's going to look like this. We're going to have several graphs that have time on the x-axis and position on the y-axis. We have used x to represent position. We could use y, we could use z. Sometimes we will use an r, and sometimes we will use a d. Today we're going to use a d to represent the position. And let's talk about just a random line. Class. The symbol for slope is. We'll try that again. I don't know if you remember, if I call it class, that means everyone, including Jimmy. Class, what's the symbol for slope? M. Okay. M is the slope. Class, what's the equation for slope?
I'm just kidding.
We'll try that one more time. This is kind of fun. Class, what's the equation for slope? There are actually two answers. I don't know how you all arrived at the same one. What's the other one? Rise over run. Okay. There are two different answers to that question. We could say slope is equal to rise over run. We can also say it's equal to change in y over change in x. Change in y over change in x implies that you have a y-axis and you have an x-axis. We have neither in this particular case. Instead of having an x-axis, we have a time axis, which means we have delta t on the bottom. And instead of having a y-axis, we have a position axis, and what we used for that generally was a delta x. So class, the slope of a position versus time graph is? No, I'm not asking you to read, I'm asking you to think here. We've already determined that. We have Cassidy, velocity. The slope of a position versus time graph is velocity. That is something that you need to know for this class. The slope of a position versus time graph is velocity. So what we're going to do now is we're going to walk through a bunch of different graphs. I'm going to draw the graph on the board, and then I'm going to call on individual students, and they will get an opportunity to come up front and to walk that graph. So we have position in meters as a function of time in seconds. We're going to set up our coordinate axes. We're going to say all of our motion is going to be along one. We're just going to have linear dimensions here. We're going to have along this, our x-axis is going to be our position. So everything's going to be along this, our position axis. We will set up this location as the middle of the desk. Right over here, this is to the right of the desk. And over here, this would be to the left of the desk. Everything is done relative to you because I can turn around. So we have on our axes here, the middle of the desk. And up here is to the right of the desk. And down here is to the left of the desk. And the first graph is going to look like this. It's a straight line that starts here and goes like that. So what I'm going to do now is going to call on one individual. That individual is going to get to come forward and walk their way through this graph. Mitch, come on forward. So Mitch, this is going to be your graph. You're going to get to, what I want you to do is I want you to say start when you start and finish or end or done or something when you are done. So you come up to the front and start. Okay, turn, face your audience. At this point, you think about how he did and you respond. You say he did everything great. He did nothing right. He did most things right, or I have absolutely no idea what he did. You respond this with the thumbs, etc. Nolan, you're not going to respond. He's thinking. Oh, he's cogitating. Okay. Mostly we have thumbs up. Thank you, sir. Go on back. You can see here, he started to the left of the desk, which was over here. As time went by, he went toward the middle of the desk, and as time went further by, he got to the right of the desk. One common interpretation of this graph is that that's not what he should have done. He should have instead started here and then climbed over Jimmy's desk and then somehow gotten right over here and maybe climbed right across here and then right over the top of Mitch. Okay? That is not a correct interpretation of this graph. For some reason, people have a tendency to look at this as a diagonal line, therefore I must move diagonally. Remember, this represents on the y-axis position and on the x-axis time. So this represents how somebody moves through time, not through two different dimensions, but not two different spatial dimensions, but one spatial dimension and one time dimension. So we're only moving along this axis right here. Don't worry, we'll do plenty more.
Do you want us to write out all these? Or?
So your question is, do I want you to have complete notes or incomplete notes? Is that the question? I thought
I mean,
that's
like, can we write it out on one thing, or do you want us to write multiple graphs?
I would suggest multiple. Let me take little notes of what happened. Whatever. Let's do one that looks like this. Kat, this is yours. Please come forward. Walk this graph for us. Please remember to say start when you start and stop when you stop.
Start and stop.
Ladies and gentlemen, people think. Respond. Thumbs up. Interesting. There's a line up there, Kat.
But my position stayed here the entire time. Over.
But my position stayed here the entire time, right? There's a line, but you didn't move. Your position is always to the right of the desk. Very good. Okay, let's look at it in terms of slope. Class, this. You're doing an excellent job. Slope. The slope of a position versus time graph class is? Velocity. What's the slope of this line? 0. So what should her velocity have been?
0.
Which is exactly what you illustrated. Very good. Thank you much. Okay. We'll do that in a minute. Okay. Let's do this. Position, again, as a function of time. Nolan, come on down. It's supposed to be a straight line, not very good. Okay, thanks. Start. Stop. Okay. Started to the right of the desk, walked through all the way to the left of the desk. Question. Did he face the correct direction when he did it? Jimmy? Irrelevant. Question, there's nothing on there about the direction he should be facing. Okay, did he go the correct direction? Yes. Okay. What is it about this graph that tells you he should have gone that direction? It's going from right to left. Sure. Give me another answer on that one. That's correct, Kat?
You have to start where the line is touching the 0 on the time, or where.
Well, that's where you would be in time. It's not. It doesn't have to do with where time is. I don't know when time started. Well, actually, I get to 14.7 billion years, but 13.7. Anyway, never mind. What, Savannah?
The line has negative slope.
The line has a negative slope. Remind me, class, the slope of a position versus time graph is? Velocity. So this is a negative velocity, so we should be moving to the left, which is a negative direction. Great. Okay. Let's do one more. Oh, it's supposed to be straight. Never good at straight lines. Yeah, it's worse. All right, perfect. All right. Cassidy, come on down. Flip-flops. Please remember to say start and stop, and please do not hurt yourself. written over there.
Start. Yeah. Stop.
Interesting.
I don't know.
No, you did fine. Come on over here. Let's talk about it for a minute. I saw some like this, very few like this. Okay, here we go. Let's start with the little things. Libby, where'd she start? Did she start at the right spot? Okay, she started at the middle. What'd she do then next, Libby?
She went to the right.
She went to the right until she got somewhere over here. What'd she do next?
She just went back.
No, she didn't do that next, actually.
She stopped.
She stopped, and you paused for a while. Agreed. What did she do after that? Not
Back over here.
Right. Did she go in the correct direction?
Yes.
Yes. Now, it's an important piece, but I don't think you went back correctly in that direction. Do people agree that that's the issue? Okay. What is the issue with that, Taku?
She should have went back faster.
Should have gone back faster. What is it about the graph that says she should have gone back faster? Because the magnitude of the slope. I'll show that on the board. Okay, you should have gone back a little bit faster. You should have run all the way in the flip-flops. I'm sure it's interesting. Okay, good. Thank you much. So she did everything correct except for this last little piece. She should have moved much faster. If you look at it, this magnitude of this slope is much less than the magnitude of this slope. Another way to look at it is she had a large amount of time to go through a small displacement, whereas here she had a short amount of time to go through a much larger displacement. Therefore, she should be moving much faster.